Alright, Science 20s, in this section we are going to introduce two new formulas that are going to help us to calculate displacement and help us to understand acceleration due to gravity, specifically acceleration due to gravity on Earth. So, let's see what this is all about. First of all, let's think about objects that are falling. So, any time where you have an object that's falling, it's not uniform motion where the speed is constant, but it's accelerated motion. And that's because if you think about the object from the moment where it's dropped till the moment when it hits the ground, it's consistently accelerating. It's speeding up and speeding up and speeding up. So if we know the acceleration that an object falls at, we can find out how long it's going to take for that object to hit the ground. So the first question we want to think about is how quickly do objects fall to the ground? So let's consider a scenario. If we have Galileo climbs up to the Leaning Tower of Pisa, although back in Galileo's day it wasn't a leaning tower, they just called it the Tower of Pisa. And he takes a cannonball and a tennis ball. He drops them both off. Which ball is going to hit the ground first? Now you'd expect that it would be the cannonball, right? Because it's heavier. And that's what people expected too in Galileo's day. But when he actually got up there, climbed to the top, dropped them off, he found that balls of different size actually hit the ground at the same time. And that's because balls like cannonballs are very aerodynamic, and they're not limited by air resistance very much. And you can think about that example. So it's not how heavy something is. Imagine a piece of paper. If I take a piece of paper and I have it, a flat piece of paper, and I drop it, it's going to float to the ground very slowly. But if I take that same piece of paper and I crumple it up into a ball, and then I drop it, it's going to drop a lot faster. It's going to accelerate more quickly, and it's going to hit the ground in a shorter amount of time. The mass of the paper has stayed the same, right? The paper hasn't gotten heavier. It's just gotten more aerodynamic. And so what we're going to do for this section of physics is, because air resistance is kind of a tricky thing to keep track of, we're going to ignore air resistance. And we're going to be working in situations where we don't have air resistance. So one situation like that, and this is what Galileo proposed, is that if you ignore air resistance, then objects in Earth's gravity field are going to fall at the same rate. And there was an important test here that was done to figure out if this was actually true in a place part of the solar system where we don't have very much air resistance, and that's the moon. And humans went to the moon during the Apollo missions, and one of the tests that was done was to see if Galileo was correct and objects would fall at the same rate if there was no air resistance.
Well, in my left hand I have a feather, in my right hand a hammer. And I guess one of the reasons we got here today was because of a gentleman named Galileo a long time ago who made a rather significant discovery about falling objects in gravity fields. And we thought that where would be a better place to confirm his findings than on the moon. And so we thought we'd try it here for you. The feather happens to be appropriately a falcon feather for our falcon. And I'll drop the two of them here, and hopefully they'll hit the ground at the same time. How about that? Mr. Galileo was correct in his findings.
And as you can see, if you don't have air resistance, a hammer and a feather will accelerate at the same rate. They'll hit the ground at the same time. On Earth, that doesn't happen. The hammer would drop faster, hit the ground sooner, but that's just because of air resistance. And so what Galileo figured out is that all objects in Earth's gravity field accelerate at the same rate, negative 9.81 meters per second squared. And this is such an important value that we give it its own unit symbol. We're going to call this value g. G is negative 9.81 meters per second squared. That is acceleration due to gravity. And you'll find that in your data book on your physics page. And so what we'll do is when we're calculating acceleration due to gravity, we can use this value instead of the A that would normally stand for acceleration. And if you're in your data booklet on the page with all of your physics formulas, and you look down, 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 right down to the bottom, so this is on page 2, you see average acceleration due to gravity on the surface of the Earth is 9.81 meters per second squared. And on that same page, you'll see the two formulas that we're going to use. These are new formulas that you haven't seen before. And they look a little bit scary when you start with them, but let's break them down and hopefully you'll see that they're not actually that bad. They're going to be pretty straightforward to work with once we kind of sort out what all the variables are and how these things are, how we're going to work with these things. So just go back to your data booklet. You can find them here. So here's the one, D, and here's the other one down here, right? So you're always going to have these when you're doing a quiz or when you're doing a test or something like that. Okay, so let's pick out the variables, and that's going to help us to kind of make sense of these things, I think. So to start with, we have a delta D. So remember the delta, that's our Greek letter here. This delta here, that just means change in. And so it's not really going to be that important to keep track of that delta when we're doing these formulas. Instead of just a displacement then, right, D with the arrow is displacement, this means a change in displacement. And really, displacement will always be a change in displacement when we're working with it in Science 20. So that's one of our first things that we want to keep track of. So what is the D? Well, the delta D for both formulas is my displacement. And the displacement is going to be measured in meters. Right, so that's going to be used for both of my two formulas. They're both solving for a displacement here. Now, what else do we have? Well, we have a VI. We've seen that before. V can either be speed or velocity. This one has a vector arrow, so it's a velocity. And it's a VI, so it's an initial velocity. And the initial velocity would be measured in meters per second. Notice that it's not meters per second squared. That's what accelerations are measured in, not in just meters per second. And you're going to see velocity in both formulas too. Now in this one, we see, this is both two, we see a time term, change in time, delta t. This one actually has two delta t's in it. This one has one. But the delta t is going to be a change in time. And because my velocity is measured in meters per second, time will be measured in seconds. Now here's where the formulas are different. So all of these guys here are going to be present in both of my formulas. All right, let's just add that as a little note. Both formulas. And then we have a term that's different in each one. So this guy has got an acceleration term. A with the vector arrow. That's acceleration. So if I know the acceleration, like something accelerating in Earth's gravity field at negative 9.81 meters per second squared, I can use that term here, and that would be measured in meters per second squared. And then this one has got a VF, final velocity, and that's not present in this formula over here. So the VF is a final velocity. and that's measured in meters per second. So I'm going to have to make some decisions about when I want to use formula number 1 and when I want to use formula number 2. But one of the things that's going to help me make that decision is whether or not I know the final velocity or do I know the acceleration. Okay, let's try a couple of problems. So Mr. Mahaffey drops a rock on a Science 20 student to get them to work harder. He drops the rock from rest and it takes 3.5 seconds to hit the ground. How high was the rock dropped from? So let's see what information I have. I dropped the rock from rest. Now, if something is being dropped from rest, that means that its initial velocity is 0. And that's a piece of information that it might not seem like you're actually being given, but you are. So the VI is 0 meters per second. It takes 3.5 seconds to hit the ground, so that's the time. 3.5 seconds. How high was the rock? Well, that's a displacement. So I'm looking for displacement, which is going to come out in meters. So it seems like those are the only numbers that I have. Let's see which of my two formulas I want to use. So I know the VI, I know the T. I'm looking for the displacement. So I look at my formula sheet. Okay, I have VI and T. Well, those are in both formulas. I'm looking for displacement, but I need one of these other things. I need the acceleration or I need the final velocity. And depending on which one I have, that's going to decide which formula I use. Now, before you panic and say, I don't have acceleration or final velocity, remember that the rock is being dropped on planet Earth. And on planet Earth, objects accelerate at a rate of 9.81 meters per second squared. So that's going to be the acceleration due to gravity, or that's going to be the G. Or we could write it as A, right? Because it is an acceleration due to gravity. That's 9.81 meters per second squared. And this is down, so it's in the negative direction. So we're going to put a negative sign on this. So that means I do have the acceleration, which means I want to use this formula, formula number 1. So let's start by writing out my formula. My displacement is equal to my initial velocity times my change in time. So VI times my delta t plus 1/2 times my acceleration times my change in time squared. And notice it's just this change in time that's squared, not this whole last term. That's going to be a common mistake. So 1/2 times my acceleration, right, which is the same as g, multiplied by my change in time squared. Now I have all these values, so I can plug in and I can solve. So my VI is 0 meters per second times my change in time, which is 3.5 seconds, plus 1/2 times g, which is negative 9.81 meters per second squared, times my change in time squared. So that's 3.5 seconds squared. Now I'll load up my calculator and let's plug this in. Now you notice I put brackets around each of my terms here. That's going to help me to organize them and make sure my calculator deals with this properly. So 0 times 3.5, close my bracket, plus 1/2. Now I can write it in as 1/2. If I do, I need a little bracket for it. I could have also put this as 0.5 times negative 9.81. I have to be sure to use the negative sign down here, not my subtract symbol. That will give me an error. And then times 3.5 squared. Then I can close my bracket. And the squared's got to be just on the 3.5, not outside the bracket. Otherwise, it's going to square this whole second term here. So what does that give me? Negative 60.086. Let's see, how many sig digs do I get? 3.5 seconds. So I get 2 sig digs. So this will round to 60. And it means that my rock was dropped from 60 meters up. The displacement ended up at minus 60. So if the displacement ended up as minus 60, that's meters. That means the rock was dropped from 60 meters up. There's my answer. Okay, let's try another one. So cannonball is dropped from 150 meters in the air. How long does it take to hit the ground? So let's see what kind of information I have. If it's dropped, that means that its initial velocity is 0 again. From 150 meters in the air, that's the displacement. How long, that's the time, does it take to hit the ground? Okay, let's collect my information. VI equals 0. My displacement is 150 meters. My time is what I'm looking for. And this is happening on Earth, we can assume, because we're not told otherwise. So that means that acceleration due to gravity, g, is negative 9.81 meters per second squared. And if the cannonball starts from 150 meters up and it falls down, it's falling in the same direction as g. So this really should be negative 2. We use negative as the down direction, typically. So how long does it take to hit the ground? Let's look back at my formulas. I know VI, D, and G, or A, and I'm looking for T. So I don't know the final velocity. I can't use this right-hand formula, so I have to use the same one again. I'm going to have to do a little bit of algebra to get T by itself, but it's not going to be as bad as we think it's going to be. So let's start by setting up the formula. My D displacement is equal to VI times change in time plus 1/2 times acceleration due to gravity times my time squared. Now, I'm trying to get time by itself, and that's really hard because I've got time in my equation twice, and here it's a regular t, and here it's t squared. So how do I deal with that? Well, if I recognize that because my initial velocity is 0, what is anything times 0? If you don't know, you can try it, right? So 0 times 5, 0, 9 times 0, 0, 88, 88, 88 times 0, 0. So that means that this term right here, my VI times delta t, this term is going to be times 0, and so it's going to cancel. It's going to go to 0. And that's going to simplify my formula a lot for me. My displacement will be equal to 1/2 times g times t squared. So now I need to get the t squared by itself. I'm going to leave the square till the very end, and I'm going to try to clear the other parts of the equation out first. So how do I get the 1/2 to cancel? Well, I can either multiply by 2, or I can divide by 1/2. Let's divide by 1/2. Because anything divided by itself is going to cancel, And I'm allowed to do that in algebra as long as I do it to the other side of the equation too. Divide by a half over here. Then I need to get the g to cancel also. So I want to divide by g over here and divide by g over here. Then these guys are going to cancel. Now let's rewrite what I have because this is getting a little confusing, and let's flip it around too. So my t squared is equal to delta d, change in displacement, divided by 1/2 times g. Now, the only thing I have to get rid of is this pesky square over here. So how do I get a square to cancel? I take the square root, because a square and a square root are opposite functions. So I take the square root of this side, that's going to cancel my square, and I'm allowed to do that as long as, if I square root this side, I have to square root this whole side over here too. And so what does that leave me with? T is equal to the square root of delta d divided by 1/2 times g. Now we could plug in my numbers. So my displacement was negative 150 meters divided by 1/2 times negative 9.81 meters per second squared. This guy on the bottom is going to need a bracket so my calculator doesn't get confused. Now let's plug in and let's solve this guy. So I'm going to deal with the square root maybe at the end. Let's just do the stuff inside the bracket first. So I need negative 150 divided by 1/2 inside its own little bracket times negative 9.81. Close my brackets. Then I can hit enter. Oops. Let's go to, did I put an extra bracket in? I think I did. Close my bracket. There we go. So 30.58. Now, I still have to square root that. So to square root it, I hit the square root button, and then I can tell my calculator to square root the answer with this button here. Then when I hit enter, I will square root that number, and here's my answer. Let's look at how many sig digs I get. I think I get 3 this time. So 5.53 is my answer. 5.53. And that's time, so the units are going to be units of seconds. Okay, we got one more. An egg is thrown downward out of a window. If the window is 11.2 meters above the ground, and it took the egg 0.550 seconds to hit the ground, what was the initial velocity of the egg? Okay, let's see what we got here. Let's start by collecting my information. See if we can line this up a little nicer. There we go. Start by collecting my information. Now, the egg here is thrown, so it means that VI is not 0. VI is what I'm looking for. What was my initial velocity? The window is 11.2 meters above the ground, so that's my displacement. And it took the egg this long, well that's a time, to hit the ground. So my displacement is negative 11.2 meters. The time it takes, 0.550 seconds. I'm looking for the initial velocity, and we know this is happening on planet Earth, so that means that g is still negative 9.81 meters per second squared. Okay, so we're looking for VI. Let's see what kind of information we've got, which of our formulas we should use. So I don't know anything about my final velocity here. I do know about acceleration, I know about VI, so this is the formula I should use again here, this formula number 1. So let's set up the formula and then let's do our algebra. because we're looking for VI, which isn't going to be what the formula is solved for. So my delta D is going to equal my initial velocity times my change in time plus 1/2 times acceleration due to gravity times my change in time squared. So what I'm looking for here is my initial velocity. So I have to get that by itself. That means I've got a whole bunch of stuff that I have to clear out and get to the other side of the equation. So let's start with this big term. This whole big term is being added. Well, if I subtract by everything in this bracket here, on this side and on this side, this whole thing is going to cancel. So I'm going to subtract 1/2 times g times delta t squared on this side and subtract by that on this side. And then this and this are going to cancel. Now let's rewrite what I've got, and I'm going to flip it left to right at the same time. So VI times delta t is equal to my displacement minus 1/2 times g times delta t squared. Almost there. I want VI by itself being multiplied by delta t, so I can divide by delta t on this side. Those will cancel. Divide by delta t on this side. Okay, finally ready to plug in some numbers. So my delta d minus 1/2 g times delta t squared divided by delta t. So let's plug in some real numbers here. My displacement was negative 11.2 meters. Let's scroll this a little bit. Can we? No. Negative 11.2 meters minus 1/2 times negative 9.81 meters per second squared times my change in time, which was 0.550 seconds squared. All of that is going to be divided by 0.550 seconds. Okay, that was a mouthful. Let's see what we get here. So, negative 11.2 minus bracket 1/2 times negative 9.81 times 0.55 squared. Then all of that we're dividing by 0.550, and that gives us negative 17.6 meters per second. This is the initial velocity. I get 3 sig digs, so it'll be negative 17 point, we have to round to this place, there's a 6 next to it, so it'll round up to negative 17.7. And we have to keep the negative because that's telling us that the direction here is in the down direction, that it's being thrown towards the ground. Negative stands for down. So my VI then is negative 17.7 meters per second. That's my initial velocity. Okay, so go on and try those problems that I've given you. There's an answer key available, and there will be 2 opportunities for you to log on to Zoom. If you need any help or you want me to work out any more examples for you, I'd be happy to do that during our Zoom meeting.